Okay. So, were there any questions about the free radical halogenations that we had done from yesterday? So what would you have to do with that on Monday? You're going to have to write the complete mechanism. And then if I give you a free radical halogenation reaction, you're going to have to give me the possible products and then tell me which one would be the major product under whatever conditions, whether it's bromination, chlorination at room temperature, or whether it's high temperature. And you'll see that on some of the older exams that are in Canvas. So maybe we'll come back and do a couple review problems here at the end. So the next topic is to pick up on what we were talking about yesterday in terms of allylic radicals. So where we ended yesterday was we said, okay, here is what is that? And why is it there? And it needs to go. So we talked yesterday about, started with the idea of what's called an allylic radical in the allylic position. So if we took this molecule and we want to free radically halogenate, we're going to free radically halogenate at that position. Okay, that's the preferred position for bromination whenever you have a double bond. And we also said, or came to the conclusion, that we can't use bromine and light for this. So if I want to do free radical halogenation, I'm going to have to use N-bromosuccinimide, and that will exclusively brominate at that allylic carbon. Okay. So if we use bromine, we'd end up adding 2 bromines across the double bond. Regardless of whether it's bromine light, bromine heat, bromine will preferentially add to the double bond, so that we'll end up with basically adding 2 bromines trans across that double bond. And that's not what we want to do if we want to do free radical halogenation. Okay. So you can think of this position as, basically that position is like a 1700 in terms of selectivity. It's probably greater than that. Okay. So this allylic system then is going to behave a little bit differently because of the double bonds. So the next thing I want to do is I want to start, so I take this molecule right here and I brominate it, and now I'm going to take this allylic bromide and I want to do an SN1 reaction with it. So I'm going to take that molecule and I'm going to treat it with water. So when I treat this with water, I automatically know this mechanism is going to go in an SN1 mechanism because water is the weak nucleophile, and the weak nucleophile can only undergo SN1. So first step in the mechanism is going to be lose the bromine to form this allylic carbocation. So just like yesterday we had an allylic radical that had resonance structures, we now have an allylic carbocation that has resonance structures. So I'm just going to write that down here so I can write them side by side. So here's my first allylic radical. What is the resonance structure of this going to look like?
Double bond for the middle bond.
Okay. And then that's going to make on the primary carbon at D on the left side. So I can write this resonance structure for this allylic carbocation. For those of you in lab or have talked about mass spectrometry in lab, this is nothing new. We just did this. Now we're going to go into a little more depth here. What would the resonance hybrid of this look like? If I'm going to write the resonance hybrid, I'm going to write all the single bonds. I'm going to average the charges. Now, actually what happens in writing these resonance hybrids is that everywhere there was a plus charge, there's going to be a delta plus charge. So there'll be a delta plus charge here, there'll be a delta plus charge there, and then there's going to be a partial double bond here and a partial double bond there. So this would be my resonance hybrid. So far, all I've done is I've lost my leaving group, which I probably should put up here, plus a Br minus. I've lost my leaving group, but now I've formed a carbocation that has resonance structures, or one resonance structure. So now I'm writing its resonance structure and the resonance hybrid. Now the water is going to attack, right? The water is going to add. And of these three species here, which one is the real structure? The hybrid is the true structure. But here's the issue with the water coming in. If I said, well, my water's going to come in and it's going to either attack that carbon or it's going to come through and it's going to attack that carbon. If I do that, then I've got to keep track of where the double bond goes. And so it's not a direct, this is not the easiest way to do the reaction. Although this is what happens. The water will attack the resonance hybrid. But to simplify things, what I can do and what I'm going to do is I'm going to treat these two resonance structures as if they were the reactants. Remember, the true intermediate is the hybrid. But it's easier for me to then say, okay, I'm going to take water and I'm going to go ahead and add it to that carbocation, and then I'm going to take water and I'm going to add it to that carbocation, so that it's easier then for me to write my final products. If I do that, remember I'm still not allowed to just add an OH. I need to add the entire water molecule so that I form the oxonium ion for each one. And then I'm going to lose the H plus to form the final OH. So I'm going to form those two species as my final product, but don't just jump right in and put the OH there. If I had you write this mechanism on Monday, which I very well could, you're going to have to add the entire water molecule, or we could crank it up a notch and say add an alcohol, which would be the same mechanism except HOH, HOR. But then I'm going to get I have to make sure I have the oxonium ion. Cameron?
Would the stability of the carbocation
Well, that's going to be the next question. That's going to be something we have to deal with in the next question. Okay. So is everybody okay with that, with how we did this? The only new step here is the additional carbocation resonance structure. Other than that, this is a straight SN1 reaction. Okay. So, now the big question then. I made two products. Which one is the major product? So which one of these two is the major product? We'll call this A, and we'll call this B. Now we're going to have a little sense of deja vu from yesterday, right? Because yesterday we made two products and I said make an argument for the one and then make an argument for the other. I'm going to do the same thing here. Which one of these is the major product? And somebody make an argument for A and somebody make an argument for B. No?
Argument for A, you could say that the carbocation is not only secondary, but it's also like the intermediate.
Okay, so the intermediate here is what kind of carbocation?
Here,
Oh, sorry. Because you can't. Let's try this, even though I'm gonna get frustrated. This one.
It's a
It's allylic.
yeah.
If I said primary, secondary, tertiary, what would you say? So this is a secondary allylic, and what kind of carbocation is this one? So primary allylic versus secondary allylic. And so your argument for A would be, and I think this is what Cameron was getting at a couple minutes ago, is that A would be the major product because, anybody can jump in if you would like, because it's coming from the more stable intermediate. And just like yesterday, I said, how many times have we done that kind of a reaction? And the answer is a lot. So that's not new. We could say A is the major product because it's coming from the more stable intermediate. Let's see, slide back. Okay. Can we make an argument for B? You want to make an argument for B? It's more substituted. What's more substituted? The double bond's more substituted, so B you would consider then to be the more stable intermediate. Now, do we have rules about stabilities of alcohols? Do we have a rule that says a primary alcohol is more stable than a secondary or vice versa? No, we don't have that rule, just like we didn't have it yesterday with the halides. We didn't say, well, primary halide's more stable than a secondary. There are no rules for that. But there are rules for double bonds. The more stable, or the more substituted the double bond, the more stable it is. Have we done reactions where we form the more stable product? That's Zaitsev. That's a Zaitsev rule. So you could make an argument for B that it's the more stable product, and so therefore I'm going to form B as my major product. So we could argue this from both sides. We could say A is going to be the major product because it comes from the more stable intermediate. B is going to be the more stable product, and it will be the major product now. So we're kind of like where we were yesterday, more stable intermediate, but there we were talking about statistics in terms of making the opposite product. So then what did I do yesterday? I said, well, what is the major product? And my initial answer was, oh, I know. It depends. And then you said, it depends on what? And what did we say yesterday? It depended on whether it was bromination or chlorination, and whether it was at room temperature or high temperature. Well, it's not, there's going to be a different set of it depends rules here for this one, but it's going to depend on the reaction conditions. I can change from one major product to another by changing the reaction conditions. Right? So, we're going to take a minute or two break here and come back to this, but this is kind of the reaction to set this up. Because I've got an allylic carbocation, I'm going to write the resonance structure, and then I'm going to try and determine, okay, which one's the major product depending on the conditions, and the first thing I have to do is define the conditions. Now, the next the next thing that I want to talk about for a moment is the idea that there are two types of dienes that we need to be aware of. Because I show you that problem to set up a conjugated diene reaction. So there are two types of dienes. A diene just means that you've got two double bonds in the molecule. Okay. 3 types. Oh yeah, that's right. The third one is, yeah, these we're gonna treat the non-conjugated one as if it's independent. But that's right, there's kind of a third one. These are the two we're gonna work with. Their terminology is a little bit different. They're Canadian. Although the guy that wrote the book is Canadian too. Every time they do something different, that's my standard line. Why does the book do this differently? Because they're Canadian.
So non-conjugated is isolated.
Yeah. Yeah. No. When the double bond's like that's like this, I think, right? Yeah. Yeah, we're not gonna worry about this one. That one leads to some non-RS chirality. So we're just going to skip it. But you can actually make chiral molecules from these double bonded species, but they have no chiral center in them. So we're just going to skip that. It still has there's 2 terms for it that I can't quite remember. But there are 2 terms for it that aren't R and S. There still is like a D and an L, because it'll still rotate plane polarized light. And there's still mirror images that are not superimposable. It's just a new type of chirality. It's not a spiro, because a spiro is one where you have the carbon attached to 4 bonds, and then you have like a ring over here and a ring over there. That's a spiro. But anyway, I digress. So we're going to do conjugated and non-conjugated, which is also called isolated. The easy thing about the isolated double bonds is they react independent of each other. So I could do I can do all the reactions that I did before on double bonds on an isolated system, and all I have to do is just remember Markovnikov, anti-Markovnikov, and since I have two double bonds here, I can react two equivalents of stuff. So if I want to react this with two HBRs, I'm going to add two HBRs Markovnikov. If I want to add two BR2s, I'm going to add two sets of BR2s. So non-conjugated systems, we've done. It's the conjugated system that is a little bit different. And the first thing about the conjugated system is it's always more stable to be conjugated than it is to be non-conjugated. So for instance, if I added a bond, so I've got the same number of carbons, I've got the same molecular formula, the conjugated system and the non-conjugated system, the conjugated system would be more stable. And experimentally, I could determine that by doing a hydrogenation reaction, and I could measure the heat of that. So for instance, I'll just, because they talk about this in the book, if I add hydrogen, if I add two H2s to each one of these two molecules, I'm going to make the same pentane molecule. Okay? So if I take these two molecules then, and I react them with H2 and palladium, I'm going to go to the same product, having the same energy. So all I do is, if I want to know if conjugated or non-conjugated it's more stable, I do hydrogenation and I measure the heat of hydrogenation. Well, which one's going to be higher in energy? The one that's less stable, because here's my energy. And so if the conjugated system is truly more stable, it'll be at a lower energy than the non-conjugated one. So if I measure my heat of hydrogenation, this heat is going to be more exothermic, and they're all heats of hydrogenation are exothermic. But the heat of hydrogenation of the less stable species is going to be more negative. It's going to be more exothermic. And so the more exothermic species is going to be less stable. Less stable also equals more reactive. So what I do is I start with the final product. If, let's say, this one was minus 100, and over here this was minus 80, then I would go up 100 units. I'd only go up 80 units. And so looking at the double bonds, I would say, okay, the conjugated system has a lower heat of hydrogenation, and so therefore it's more stable than the one that has the higher heat of hydrogenation. It's the less stable, more reactive principle. And so they talk about this. You could also combust these and do the same thing, since you're going to make the same amount of CO2 and water. So that's how we know that the conjugated system is more stable than a non-conjugated system. And the reason for this is because there's a partial overlap in that single bond between the two double bonds. And the reason for the partial overlap is because all four of those carbons in the carbon-carbon double bond are sp2 hybridized, and all the p orbitals are lined up parallel to each other, so there's a little bit of overlap of those two p orbitals in the sigma bond, or in the single bond. And so that single bond has a tiny bit of sort of a double bond character. What it really means is it means that it's shorter. So that partial overlap then gives us a more stable conjugated system that experimentally has been known for a number of years. And it's only been within the last, I think, I'm trying to remember when Norm talked about this. But there's a retired physical chemistry professor over at Oberlin. And by using super high resolution NMR, or not NMR, super high resolution IR, they were able to show experimentally, working with a group in Germany, that this bond is actually shorter than a normal single bond. And nobody had shown that experimentally. It was known theoretically. It was known that it was more stable, but so it's only been within the last 15 years, and Oberlin only has undergraduate students, so there were undergraduate students working on that project. So their undergraduate research project was like to prove something that's been accepted in organic chemistry textbooks for the last 50 years. But they finally had the experimental data to show that that was really the case, within uncertainties and all of that. So that's now known. And it's known by, like I said, another university short place away. So conjugated systems are going to react differently than non-conjugated ones, okay, which is what this whole thing is about. So when we have the opportunity, it's more stable to form a conjugated double bond than it is an isolated one, or a non-conjugated one. In isolated ones, we can do all those reactions. Okay. Now, would that bring those reactions all in on the next test? It could, right? Because when I say we can do all those reactions, now all of a sudden they're fair game for the next test. But maybe not. Let's focus on the conjugated system, because you're going to find some similarities with the conjugated system. Okay. Guys, are you kind of with me? You make it through the forest. Maybe we kind of got off the path. Maybe you almost went over the cliff. So the reason that the conjugated system is different is because if I do this, let's say I take this conjugated system and I add HBr to it, I actually get two different products. I'm going to get this product, and I'm going to get that product. And I might as well I'm going to put numbers in here, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. Okay. So when you do this reaction, you get two different products. The first one we understand, right? Markovnikov addition of HBr to the first double bond. Where did the second product come from? Well, we need to do the mechanism to figure out where that product came from. These products are typically called, so the conjugated system is always going to have four carbons in it for the two double bonds that are conjugated. So we always number these 1, 2, 3, 4. That is not an IUPAC numbering scheme. That is a conjugated diene numbering scheme. So that we'll call the product where we added the electrophile and the nucleophile to carbons 1 and 2, the 1,2 product. And when we added the bless you. And when we added it to the 1,4, when we added the electrophile and nucleophile and they end up in the 1,4 positions, we're going to call that the 1,4 product. So when we react things with dienes, meaning HBr, Br2, H plus water, H plus alcohol, when we do these reactions, we're going to end up with a 1,2 product and a 1,4 product. The 1,4 product is going to have the double bond move between carbons 2 and 3. Okay. So we can actually write the product of any one of these reactions if we just remember 1,2, no problem, 1,4, just make sure we put the double bond between carbons 2 and 3. So the real question is, how do we make these two products? Right? Get ready for a sense of deja vu. Okay. First thing I'm going to do is I'm going to add H plus to carbon 1. In this case, we would say carbon 1 is definitely, that's the way we would do Markovnikov addition. Carbon 1 has 2 hydrogens, carbon 2 in the diene has 1. So we're going to do Markovnikov addition. So I'm going to add H to carbon 1. And so I'm going to make that carbocation. Anybody's sense of deja vu coming in? So what am I going to do now? I'm just doing the mechanism. So what's going to happen? What do I have here? What is this? And what kind of carbocation? Allylic. So I just made an allylic carbocation. So what should I do with that allylic carbocation? Write its other resonance structure. So take this pair of electrons, move it here, and write the second resonance structure. Which one is more stable? The one on the left? The one on the right? Which one's more stable? The carbocation on the left, carbocation on the right? Okay, so you want to make we want to make an argument for both. That's a good point. So argument for the one on the left. It's a secondary carbocation. Argument for the one on the right. A more substituted double bond. We kind of glossed over that, didn't we, last time? We just accepted that the secondary carbocation was more stable than the primary one. Although in that case, in that case the double bond had the same number of things in both molecules, right? If we went back to that, well, actually, no, it didn't. This double bond was more substituted than this one, but nobody made that point. But we did down here, actually, right? We did down there. We didn't make that argument up here. Okay. Well, now we got to deal with it since it's been brought up. So we got secondary versus primary, and less substitute double bond versus more substitute double bond. So here's what we need. We need a rule. What's more important to stability? Carbocation type or double bond substitution? That would be my rule. The carbocation, the type of carbocation you have is more important than the double bond stability. So that's the rule we're going to use. Okay. That's the rule. And is there experimental evidence for that? Yes. But remember, while I'm going to react each one of these, what is the true intermediate of this reaction? The resonance hybrid. So a delta plus here, a delta plus here, partial double bond. So that's the true resonance hybrid. Yeah. The type of carbocation, meaning tertiary greater, more stable than secondary, more stable than primary, is always going to be more important to the stability than double bond substitution. Oh, no. We haven't dealt with conditions yet. We're now saying that we're going to consider the secondary carbocation to be a more stable intermediate than the primary. That a secondary allylic is more stable than a primary allylic. Because we're going to do exactly what we did before, which is we need to write our products. Then I'm going to ask you what the more stable product is, and then I'm going to say what's the major product, and then nobody's going to answer, so I'll just say it depends, and then you're going to say it depends on what, and then we're right back to where we were before. Okay. So the reason I showed you the example before was because this is what I'm really after. And what I'm really after this is to put the double bonds in a benzene ring and then do the reaction. So we're stepping our way through this.
It's like the next step in the reaction. Like the reactants can't see the product. So
Right.
It's looking towards the intermediate, so we need one to only more stable intermediate before it comes to one stable product. And
Yes.
one intermediate.
Yes, but there's another piece to this that we're going to come to. So there is another piece. Yes, it's and actually let's work through that. So here's my resonance structure, right? This is my resonance structure of those two, and this is what really reacts. So I'm going to have to take that into account when I make my explanation that's going to deal with your issue of how are we going to get to the final product, and the fact that I'm going to start with this hybrid. So if you're sitting at the hybrid, the real question is, where's my BR going to react? Is my BR going to react with this carbon, or is it going to react with that carbon? And the answer is both, but in one set of conditions, it's going to preferentially react with one, and in another set of conditions, it's going to preferentially react with the other. So we're working our way up through there. That's good. That's a question we had to answer, but we're working our way through it. Or I'm working my way through it. And you're just along for the ride. Okay. So we didn't deal with this last time, with the last example, but the carbocation stability will outrank the double bond. That's the most important. So tertiary, more stable secondary, more stable primary, doesn't matter what the double bond is. But now what am I going to do? I'm going to do what I did before, which is I'm going to take the Br minus and have it come in and add to the carbocation. So now I'm going to end up with the Br adding to the secondary allylic. And then over here, my Br is going to come in, and it's now going to add to the primary allylic. And so now I've made my 1, 2 and my 1, 4 products. So where did the 1, 4 product come from? The second resonance structure of the allylic carbocation. So why did I do the first one? Because that was the introduction to this. What we did there, we just did here. All right? So which one is the major product? See, just like I predicted, nobody answered. It depends. It's going to depend on temperature. It's going to depend on time. So actually, those are the two things it's going to depend on. Whether my reaction goes for 5 minutes or 5 hours, whether I do it at low temperature or high temperature. That's going to be an element of this as well. So all those things are going to come into play. Okay. So everybody with me before we take that, because it's going to involve an energy coordinate diagram. And it's going to answer your question about, well, I didn't ask this, which one's the more stable product? Now there's no carbocation to worry about. Nope, it doesn't depend. Because there's no carbocation here. And we don't have rules about primary, secondary, tertiary bromides. So the one on the right is going to be the more stable product because the double bond is more substituted. Okay. So I now have the more stable intermediate producing the less stable product, and the less stable intermediate producing the more stable product. It's going to depend, the conditions are going to dictate which one I get. Right. In general, this is the more stable intermediate. This is the more stable product. I now have a situation where right, the major product still depends, but this is, so I can set the conditions up to make the less stable product. Yeah, sorry, I didn't understand that. So yeah, I can still set the conditions up and make the less stable product. And that less stable product is going to come from the more stable intermediate. So just what we've done in the past is we've said we have reactions where you form the more stable product as the major one. We have reactions where you form the major product from the more stable intermediate. And now we have the situation where I could go either way. And so what's going to tip the balance? The conditions. Okay. And so those conditions are going to be reaction time and temperature. Right. So let me start with the true resonance hybrid intermediate. So I'm going to start with the resonance hybrid intermediate in the middle. So I'm going to have a hydrogen attached to the carbon, and I'm going to have a delta plus charge here, a delta plus charge here, and the partial bonds, and then my 3 hydrogens. So I'm going to start with that intermediate. And I'm going to have to think about this in a slightly different way. And I could ask this question, but we're going to have to remember when we went back on day 1 to the triangular intermediate of either the bromonium ion or the epoxide ion, and which carbon had the greatest delta positive charge. So if you remember, we had something like this where we had a partial bond to this carbon, partial bond to that carbon. We had 2 methyl groups here, so we had a delta positive. We had 2 hydrogens there, and we had a delta positive, and I asked you which nucleophile is going to react with which carbon. Right, that was a long time ago. Actually, I just should say that was a lot of stuff ago. A lot of stuff in between then and now. So I could say if the bromine's going to react, which carbon is it going to react with? And what I should probably say is this. I'm going to react the Br minus with both of the carbons. So I'm going to react it with I'm going to react it with 2, and I'm going to react it with 4. Okay. So which carbon, I have to be very careful as I ask this question, which carbon is the bromine going to react with fastest? Carbon 2 or carbon 4?
Is it the chart or the secondary reactions faster?
Okay, well, that's for free radical halogenation, but we still have a secondary versus a primary system here. So the same thing could be true. So which one is it going to react fastest with, do you think? Okay, that's a good argument. So the argument is it'll react with 2 faster because 2 has the greater delta positive because it's secondary versus 4, which is a primary. I might have added a little bit to your argument, but yeah. Does that sound like a good argument, Megan? And that's what's going to be the consequence of it having a greater delta positive charge. Now, you could make an argument for 4, probably based on sterics, but in this case, it's really going to depend on the amount of delta positive charge. Because basically, we're doing an SN1 reaction, right? We're doing a 1 reaction. We're doing a 1 reaction because it involves a carbocation. So the bromine is going to add, if the bromine adds to carbon 2, we're going to have a lower activation energy than if it adds to carbon 1. So the transition state energies for adding to carbon 4, the transition state energy for adding the bromine to carbon 4 is going to be higher than the energy in adding to carbon 2 because carbon 2 has more delta positive charge. So this will be lower because carbon 2 has greater delta positive charge. So that's how that translates. Greater delta positive charge means, well, in the transition state, if you're reacting a +1 with a -1, the more delta positive charge you have, the closer you are to neutral, the more stable your transition state. So which one am I going to form faster? Which way am I going, left or right? I'm going left faster. So this reaction is going to be faster. Arrhenius equation, lower activation. And so your point, Cameron, about the intermediate is not able to see the final product because all it sees is two mountains in front of it is absolutely correct. So the intermediate only sees the level, only sees the mountains, the energy barriers in front of it. It's going to overcome the one to the left faster than the one to the right. So now I'm going to go on and I'm going to make my product. So if I make my product, it's going to be the 1,2 product. Right? So there's my 1,2 product. Now over here, on this side, I'm going to make the 1,4 product. But the 1,4 product is actually going to be lower in energy because the 1,4 product is more stable than the product, than the 1,2 product, because it's more substituted. Don't agree? The x-coordinate is reaction progress. But what I'm doing is I'm actually taking, I could write each one of these as their own reaction, but I'm combining them so that, because reaction coordinate diagrams aren't a simple, they aren't in simple two-dimensional space. If you're, it's like real life. You're in the valley and you have like 5 mountains you can go over. That's kind of, this one just has 2 it can go over. So it's either going to go over to the one on the left. So the reaction progress from here to here, and then there's also reaction progress from here to here. So going from reactants to products, except the reactant, I'm starting at the intermediate, since the intermediate is common for both pathways. Still kind of with me here? Okay. Let's deal with a factor, reaction factor, or reaction condition number 1. Let's deal with time. And your choices are short time, long time. So if I react this a short time, what product's going to be favored? The 1,2 or the 1,4? The 1,2. Short reaction time, I'm going to favor the 1,2 product. Why? Because the 1,2 product is formed fastest because it has the lower activation energy. So if I react this a short time, I'm going to make more 1,2 than 1,4. How about temperature? If I want to maximize the amount of 1,2 product that's formed, what should I use? High temperature or low temperature? Low? I want to use a low temperature. Why? Okay, so if I can get just that right amount of energy to get it to overcome the left barrier, but not the right one. So that means if I lower the temperature down, what am I going to favor? 1,2. So if I have short reaction time, and I would also say a lower temperature is going to favor the left-hand product. Does that make sense so far? So far, we've formed the intermediate, which is the resonance hybrid. It can go either way, but initially, we're going to form 1,2 more than 1,4. And I can favor more 1,2 and 1,4 products by running the reaction a short time and lowering the temperature. And this sort of piggybacks on what we talked about yesterday in terms of the birds, hikers, why the free radical reactions were more or less selective. Okay, so from that standpoint, this is actually pretty good because they're right on top of each other, same principles that I'm using, sort of. Pretty close. Okay. So now the big question is, how can I ever make the 1,4 product the major product if most of it's going to the 1,2 condition? Okay, that was going to be a rhetorical question, but you can take a shot. Well, let's deal with the high temp first. So if I raise the temperature up like I did yesterday, can I form more 1,4 product?
Yeah, more than low temperature.
Exactly. So if I raise the temperature up, I'm going to form 1,4, but not exclusively. I'm still going to get, what's the best I could do? The best I could do is supersonic birds, right? They overcome the barrier at the same time, so the best I can do is 50-50. Yeah, I can do better than that. So, from yesterday, the supersonic birds from... Oh yeah, that's true. Because they can drag the hikers over the mountain. No, the dragons and birds will not be on the test. It's just again, humor's supposed to lessen the amount that you can learn in a period. I don't know, it's science. Apparently every joke is something that leaves your head. Well, I know, people argue that. Brandon, you had a question?
I was going to say, would it be when you raise the temperature, and since to raise 1,4, the product itself has a lower?
That's going to come into play. So that is important, the fact that the 1,4 product, bless you, is a lower energy. But here's the critical part that I haven't said yet. So far, we've been just going from the intermediate to the products. Can this product go back to the intermediate? What did we do in our first reaction that we did? We took this bromide, and what did I do? I lost the bromide to form the carbocation intermediate. Can I do that with each one of these products that I just formed? Could I break this carbon-bromine bond and go back over the barrier to the intermediate? Could I break this carbon-bromine bond and go back to the intermediate? Yes. So what's new about this reaction is that this is reversible. So once I form the 1,2 product, the 1,2 product could lose a bromine and go back, but here's the activation energy of the reverse reaction. Now, before the activation energy of the forward reaction was smaller than it is of the reverse. Yeah.
So, I noticed where you get really high, so it's in between, like, so it's greater than that activation energy, it's lower than the activation energy on the right side, then the product coming up will go back to the right.
Exactly. So let's do the same thing on the right-hand side. So here's my activation energy for the reverse, and then here was my activation energy for the forward. So given a sufficient energy, which reverse reaction is going to be faster? So if I have enough energy for both reverse reactions, which one's going to occur faster? The left going into the intermediate is going to occur faster than the one on the right going to the intermediate. And the reason for the difference in activation energy is because the product on the right is more stable and at a lower energy, which makes that activation energy bigger. Okay. So what's changing this characteristic of this reaction, and this is different than what we talked about yesterday with free radicals, because the free radical reaction, once you were at the product, you were done. You weren't going to break apart and form a radical again. In this system, I can reverse. So our short reaction time with a low temperature, what happens? It favors the left mechanism. Because there's not enough energy for the, because if I find that, again, sweet spot, then I can get it to stay at 1,2 but not be able to overcome the barrier to go back to the beginning. Now, will I get a little 1,4 product? Yes. Because remember, kinetic energies, there's that whole Boltzmann diagram of molecules at different temperatures. So there's a few high-speed molecules that have a lot of kinetic energy, and there's some ones that have really low kinetic energy, so there's a distribution. And that's really what we're talking about, is collisions causing this process to occur. So if I now do the reverse, and I say, how about a long time? How about high temp? So short time, low temperatures, I'm going to favor in this case, the 1,2 product. Okay. And that, in this case, is important because I'm not going to say it. So in this case, it favors the product on the left. If I go with long time and high temperature, what happens? It's gonna basically, initially it may form more 1,2 product, but then that 1,2 product's gonna reverse, and it may end up going back to 1,2, and then it may reverse, and then once it goes over the big barrier to go down into the deep well, it may not come back out. If you have a temperature that's just sufficient enough to overcome 3 of those barriers, but not the big 4th one. So in other words, it can reverse itself all day long, forming 1,2, but once it goes to the 1,4, it's stuck. That's what you would sometimes call like a thermodynamics sink. Once it goes in, it's not coming out. So if you let the reaction go for a long time at high temperatures, you're now going to favor the 1,4 product. Bless you. Does that make sense?
Why do you need that high temperature?
Because the high temperature, because I've got to overcome this barrier. So this barrier is going to require high temp to reverse itself. So I need the high temperature to reverse it, and then once it goes over this barrier, it's going to be down here, and it's probably not going to get back out again. Or it's less likely to get back out. So initially you form a lot of 1,2, and then you begin to form more 1,4 and more 1,4 and more 1,4. So that's why these two sets of conditions go together. Short reaction time, low temp, long time, high temperature. Okay. Is that everybody kind of with me? So now let's apply a terminology to this. The product that's formed with the lower temperature and the shorter reaction time is going to be called the kinetic product. And why is it called the kinetic product? Because it's the product that's formed fastest. And the product that comes from the more stable product is going to be called the thermodynamic product. And it's the product that's formed long time, high temperatures. Now I got two things to add to this. What is the thermodynamic product? It is the product that's more stable. Where does the kinetic product come from? The more stable intermediate. And that's the way we're going to define this. The kinetic product is the one that comes from the more stable intermediate. The thermodynamic product is the more stable product. Okay. I am not going to define this and say the kinetic product is, I'm not going to say it. I'm just going to say comes from the more stable intermediate. So we should probably take a jump back here because this is what we started with. Brilliantly, I might add, right? This whole sequence has been just, I mean, this is textbook. Should record it and have people watch it. Yeah. Oh, it'll get posted, but nobody will comment on it. But it'll be used. I need to monetize it, which I can't do. So let's go back here. So yeah, this is where I introduced the idea of what's the major product? Well, it depends. Now this is a good example because what I don't have is I don't have any 1, 2, and 1, 4. And notice that I never connected 1, 2, and 1, 4 to kinetic or thermodynamic. That was what I was not going to say. I never made that connection. And the reason I never made that connection was it's going to depend on the reaction, because one reaction, the 1, 2 might be kinetic, but another reaction, the 1, 2 might be thermodynamic. So that's why we're always going to define this based on more stable intermediate, more stable product. So if I go back here, which one of these two products is the thermodynamic product? B, because it came from the most stable product. So now I can come back here and I can say, well, that's the thermodynamic product. Now, does that mean that the other one is automatically the kinetic product? And not always, but let's check. So which one of these two the secondary allylic or the primary allylic? Which one was the more stable intermediate? The secondary one, and so that makes this product the kinetic product. Yeah.
The product that's more stable also has the more stable.
You would call it nothing, because the whole idea of kinetic and thermodynamic is that you have two products that you can form, and you can switch which one is the major product by switching the reaction conditions. And if you can't do that, if you only get one product, there is no kinetic or thermodynamic product, because you get the same product either way. Now, when is that going to happen? That's very rare. But then you might say, well, if it's rare, then that's the one you're going to put on the test. Could be. But what it means is, basically, if I had somehow had a symmetrical molecule where the kinetic and the thermodynamic product were exactly the same, then I can't switch products. I've only got one product to choose from. And that's not that difficult to make, which I'll show you. So we go back here, which one's kinetic, which one's thermodynamic. Again, we use those basic definitions. So that means that if I ran this reaction at low temperatures for a short reaction time, I would favor product A. If I used a high temperature long time, I would get product B. And I could literally switch those two products by changing the reaction conditions. It will, as long as our reaction conditions are short, low temperature. I should make this a take-home quiz problem, but you could draw the exact same diagram starting here you could draw that exact same reaction coordinate diagram from this. And you would end up with the more stable product, lower in energy than the kinetic product, and so you would have all the same features of reversibility. No?
So, when we do, we have to know that we have to be able to draw what we do.
Yes.
Diagram, or should we know that?
Well, no, you wouldn't have to draw the diagram.
Know that it kind of fast or short time.
Well, first you got to identify the kinetic product and the thermodynamic product. So there's a couple ways I can do this. Couple of different types of questions. And if you go, and again, if you look at the older exams, you'll see the different ways I can approach this. So let's say I approach it this way. So, a couple ways I could ask this question. First, I could ask this question and say, write the 1, 2, 1, 4 products, and which one would be the major product under high temperature, long reaction times. So I could say that. I could say long time, high temp. And I could say write both products and circle the major product. Now, before you do that, let me ask a question. What's the electrophile that I'm adding? That's going to be the nucleophile, the electrophile. What am I going to add to the double bond? H+. Here's my question. Where are you going to add H+? Which carbon are you going to add it to? 1, 2, 3, or 4? Don't talk you into out of your answer. So don't let her, to her, not to let you talk her out of her answer if it's correct or not correct. Hold up. 1, 2, 3, or 4. What do we think? 2 and 3? Yeah, so I guess your choices are number 1 or number 2. How about that? All right. Somebody tell me why they chose 1. So if I add the H to the, carbon 1, I'm going to end up with this carbocation. If I add the H to carbon 2, I'm going to end up with that carbocation. That's exactly what Alex said. Add it Markovnikov. So which one of these is Markovnikov addition? What definition of Markovnikov are we using? The strict Markovnikov definition, which says you add the H to the carbon with the most hydrogens? Or kind of the modified one, which says you add the H to the carbon that forms the most stable carbocation intermediate? They're not in this case. Or are they? They are.
No, because that one's over
Two
the
has-
balance function.
Yeah, two. We're on the right because we got the
Right.
Is it the
and two
most
has an
stable
H on it.
function?
One does. So two, you're adding it on top of the H definition, and then also comes the most stable carbocation.
It's not the most stable. Yeah, but the other one is. Isn't that most stable?
I don't know. Is there something else I can do with this? Let's write the resonance structure of this. Oh, I thought I used that when we were adding the BR plus. Oh, I never used that? Okay, now I'm using it. You can also define Markovnikov addition as adding the electrophile to give you the most stable carbocation intermediate. Why not? You don't like that? I like that because it works more times than not. So I guess this would be the perfect time to make that new definition, so I just made it. It worked for that too, didn't it? When it always works except in this case. This is an exception because what you guys were arguing over there, and I'm sure everybody else looking on in amusement, but which one of these two intermediates is the most stable? The allylic or the tertiary? Because as Nell said, it has everything, right? Or did you say it's got it all? Oh, she said it all. Okay, that's okay. We're allowed to add personal characteristics to molecules. So if we're just looking in this case at the tertiary carbocation, I have one on the right and one on the left. Right? Yes? But I have an additional resonance structure. So if you're saying, well, tertiary carbocation, but I have a resonance structure that's a tertiary carbocation. So that cancels. And then I have my initial carbocation that was secondary. So in this case, where am I going to add the H+? I'm going to add the H+ to carbon 1. Why? Because I'll always then form a carbocation that has an additional resonance structure.
So is that in the definition?
So that is going to always be the more stable intermediate. So we're going to add the H plus to give us the more stable intermediate. And I'm going to go a step further now for this reaction, and say when I'm going to write the products, I'm always going to write a 1,2 and a 1,4 product, which kind of gets to Max what you were saying. If I add to carbon 2, how do I get a 1,2 and a 1,4 product? I can't. And so the other rule I'm going to now make is you always add to either carbon number 1 or carbon number 4. I'm going to make things simple. These are always going to be symmetrical dienes, so that whether you add to carbon 1 or carbon 4, you're going to get the same product. So we always add to the end of the diene system. The diene system being the 4 carbons. So we're going to always add to the end. We're always going to add to the end. And I feel fairly confident in making that rule. Which rule? So, okay, new rule number 1. You're always going to add the electrophile to the end of the double bond that gives you the most stable intermediate, the most stable carbocation. That does not negate everything we've learned to this point. That's just another way of stating it. But when we do dienes, we're always going to add to carbon 1 of the diene.
Or is that carbon 1?
Any electrophile. Because I could write 1,2, 1,4 if I added bromine. I would add 1 bromine to carbon 1, then the other bromine to carbon 2, then for the other product, bromine to carbon 1, bromine to carbon 4, double bond between 2 and 3. Bless you. So always add the electrophile to carbon 1, carbon 4, always add it to the end. Because then you're going to get the allylic carbocation, you're going to get the most stable one. That's why I ask this molecule. There's another reason why I'm going to ask this molecule. So does that make sense to everybody? I mean, there's a little more argument than what normally happens. Normally it's not like 30 people arguing amongst themselves, although that wouldn't be bad. But at 8 o'clock in the morning, people are not, well, you're at 9, but still. Let's finish this up and write the product. There's my 1,4 product, and this one up here will give me my here's my 1,2 product, and here's my 1,4 product. So I added the H on carbon 1, and I add the Br on 2, and the H carbon 1, carbon 4 with a double bond in between. And basically what I'm missing in my mechanism is I'm missing my Br minus adding to the carbocation, my Br minus down here adding to the carbocation, and the only other thing I'm missing for the mechanism is the resonance hybrid. And the resonance hybrid would have the hydrogen here, and then delta plus, delta plus. That would be the resonance hybrid. So I've added the H to carbon 1, delta plus on 2 and 4, double bonds between 2 all the way to 4. No, this is just the intermediates hybrid. So there is the final product's the final product. If you're asking about transition states, we haven't been doing transition states because we could do transition states for this, but we're just going to do the intermediates. So like the last exam, if I give you a mechanism, you're just going to write the intermediates, not the transition states. So this would be the complete mechanism, except one final question. Because I would say write the complete mechanism for 1, 2, and 1, 4 for forming the 1, 2, 1, 4 products. I would probably ask you to label the 1, 2, 1, 4 products. That's a piece of cake. Hopefully. And then my final question would be label the kinetic and thermodynamic products. So in this case, who is the kinetic product? Who is the thermodynamic product? Hold on. So give me, your choices are 1, 2, 1, 4. Which one is the, what did I say, thermodynamic product? Which one's the thermodynamic product, 1, 2, or 1, 4? Fingers, please. 1, 2, or 1, 4? No, thermodynamic. Which one's a thermodynamic product, 1, 2, or 1, 4? I see 2's over here, and then I see like 4's there. Which one is the most stable product? Which double bond is most substituted? 1, 2, or 1, 4? The 1, 2 has the most substitution, right? Because around the double bond there's 1, 2, 3 alkyl groups, and down here there's, if I put in the hydrogens, there's only 2. So this is the more stable product, more substituted product. This is the thermodynamic product. Yeah, and 99 times out of 100, if you identify the kinetic product, the thermodynamic product is going to be the other one. What you have to guard against is that 1% that makes a good exam question. Right. But actually, yes, if you identify the kinetic one, then I would always check to make sure that the double bond's more substituted in the thermodynamic. I mean, when I sit down and do the exam, I'm not going through my bag of trick questions, because there really are no trick questions. These are just kind of the exceptions that make you think. I know, trick question, but still, there is no real trick question. So yes, it will typically be the other one, but I would just double check. So then the kinetic product's going to be the one that came from the more stable intermediate, and that's going to be this one. So whichever way you want to do it, that's fine. And so the thing to remember is, where's the bromine? Wherever the bromine ends up, that was the carbocation. So it is possible to work back, to write the 1, 2, and 1, 4 products if you just want to write the math and say, here's the 1, 2, 1, here's the 1, 4 product. Then break the bromine off to form the carbocation, and then you've got the 2 resonance structures. So if adding to carbon 1, if that doesn't quite make sense, you can always write the 2 products and then lose the bromine. So that's the kinetic and thermodynamics of 1214. Does that make sense? Okay, that's reaction 1 of dienes. So let's take our break and we'll start up like at 10:46 or so. And then we'll do reaction number 2 of dienes, which is the Diels-Alder. Okay, so here's the second important reaction of dienes. Diels-Alder reactions. Well, then you'll learn about it before lab today. Well, what not to do. So Diels-Alder, yes. So this is a paracyclic reaction. This is the only one we're going to learn about. We don't have to know the other ones, the 2 plus 2 and 2 plus 4 and that. We're just going to do a 4 plus 2. Yeah, we're just going to do a Diels-Alder, which is a 4 plus 2, if you read that in the book. So Diels-Alders require a diene, and they require an alkene, which is sometimes called the dienophile. And the book goes into details about whether an electron donating or an electron withdrawing group should go on each one of these. We'll learn more about electron donating and withdrawing groups next week with benzene rings. So right now we don't really know what those are. I haven't formally defined them, and I'm not going to at the moment. So in your Diels-Alder reaction, you're going to make a ring and 2 carbon-carbon bonds. So Diels and Alder, Kurt Alder and Otto Diels. Kurt Alder was one of the first real American organic chemists to achieve prominence, because organic chemistry is basically a German science. It was developed mostly in Germany before World War II, when all the scientists either came to the U.S. or got killed. So, yes. Well, I mean, if you're looking at 1700s up to, I mean, who was the most prominent? The late 1700s, who was the most prominent? Probably would be Benjamin Franklin. Maybe Joseph Priestley, who did some gas law work. But Priestley was also, I think, a minister in one of the early churches. So he had sort of a dual role. He was both a scientist and a minister. But Benjamin Franklin probably was the scientist inventor of note. So I mean, in the early parts of the early 1800s, let's see. I mean, the U.S. was like getting established. Mid 1800s, Civil War. So, I mean, this was developed in Germany. Why Germany? Germany didn't have, if you think, let's see, 1800s or so, we started to have oil impacting as our energy source. Before that, it was mostly whale oil and stuff like that. So once we struck oil in Titusville, Pennsylvania, which is across the border, Drake's Well, it's The whole part of western Pennsylvania was like the leading oil producer in the world at one point. All these little tiny towns. And I'm from there, so I know all the little tiny towns. So once you started having crude oil, then you started being able to make kerosene out of it. That's John Rockefeller in Cleveland, right? The refineries, all the Rockefeller stuff, pipelines. So we really didn't, we started to build an energy infrastructure. All Germany had was coal. They didn't have crude oil and other energy sources. So only having coal, then you've got to learn reactions in order to get the molecules out of coal, in order to get the energy basically, and other products. It's an older society, but England played a role. Obviously, all the gas stuff. France with Lavoisier and them, until they cut Lavoisier's head off in the French Revolution. So I mean, there's a whole. Somebody at one point we were talking about creating a science. We have linked classes here at John Carroll where we've got 2 classes that share a theme, but they're separate subjects. So like a chemistry, like a history chemistry class, and then the history of what was going on in society at the time. Somebody in the history department talked to me about making that class, and I just haven't followed through. But there's a lot of stuff that went into it. So Germany was basically almost completely landlocked, and it needed energy, and so that's where the chemistry developed, and also in England. But the organic, because they had that rich source of organic materials in terms of coal, so a lot of aromatic chemistry came into play. There's a lot of Russian chemistry too, but we don't know necessarily. That didn't become public, because Russia was, Stalin, and so there wasn't a lot of openness. Same thing would be true of China. Whatever was developed in China, you didn't have the free flow of information out of that. So that's why some of our Zaitsev was Russian, Markovnikov was Russian. A lot of this stuff like Diels was German, but Diels-Alder was one of his students. So anyway, that's mostly why it developed in German. And there was a time when you went to graduate school that you had to have a working knowledge of German if you were going to do organic. Which is why I took 1 semester of German my second semester of my senior year. And then they dropped the requirement when I got to grad school. So my German is limited. It would not have passed for the John Carroll requirement for a foreign language. But that's why I went to a state school. Okay, so Diels-Alder. What you do is you take the diene and the alkene, you react them this way, and the arrows can go in either clockwise or counterclockwise direction, but basically I'm going to form a carbon-carbon bond. This carbon-carbon bond is going to be used to form the second one, and then this pair of electrons will move to form a new double bond. I like to number my diene from 1 to 4 and my alkene from 5 and 6. Because what I'm going to do is I'm going to make my final product is going to be a 6-membered ring with carbons 1, 2, 3, and 4, and then 5 and 6, and the double bond will always be formed between carbons 2 and 3. In terms of the transition state, you're going to have partial bonds to the carbon bonds you're forming, and then you're going to have a partial bond here and here, there, and there. So basically you have partial bonds all the way around the 6-membered ring. That's a transition state. And there are other types of reactions that have electron movements like this. This is technically what's called a 4+2 addition, because I'm using a 4-carbon chain or 4 pi electrons adding to 2 pi electrons, or adding to 2 carbons. There's also 2 plus 2. There's some other ones that you can use light with. There's some that are forbidden, that can't happen because they're quantum mechanically forbidden. So this is just the example of a 4 plus 2. Now the way this works is that if I draw out my diene, I'm going to have all sp2 hybridized carbons with those p orbitals, and then down below I'm going to have my alkene with its p orbitals. And so what happens is that basically you overlap those bottom and top half of the p orbitals, and you end up forming the 6-membered ring. So if this is my alkene, my 4 carbons of my alkene, or of my diene, and my 2 of my alkene, it's kind of like the diene just comes down and plops right on top of the double bond. And that has certain stereochemistry implications, but that's how the Diels-Alder transition state works. So today in lab we're generating the butadiene by heating a molecule and having it decompose, and then we're going to react it with another alkene that has other groups off of carbons 5 and 6. And again, the reason I number these 1, 2, 3, 4, 5, 6 is so that if there are other groups there, I know where to put them. But the double bond always ends up between 2 and 3. So a ring and 2 double bonds, or in a ring with 2 carbon-carbon bonds. That's why Diels-Alder have the reaction named after them. That's also why they won the Nobel Prize. Carbon-carbon bond formation is the premium, and if you can form 2 in a ring, you get 2 Nobel Prizes. So that's what they did. So what about this reaction? What are the rules for this? Basically, I'm always going to start with a diene, and I could attach different groups to the diene. I'm not going to today. I could attach different groups to the alkene, which is actually going to be important. So let's say I added, sometimes I'll add 2 CNs here. I can add pretty much anything, although it should be either an electron donating or withdrawing group, but since we don't know about that, we'll play ignorant. Now, rule number 1 is that this diene must be in the S-cis conformation. What does that mean? Here's my sigma bond, and the S stands for sigma. So I have to orient the diene so that's in this U shape. Because if it's not in that U shape, the orbitals on carbons 1 and 4 will not be at the perfect distance to overlap with the alkene. So this would be an S-cis conformation. This would be an S-trans conformation. The S-trans conformation, these 2 ends of the molecule are too far away to plop down on top of the alkene. So the molecule must be in the S-cis conformation. Is that a big deal? Not necessarily. It's going to depend on like what groups are here. So I might have to heat it up a little bit to get it to completely become planar. But assuming that I don't have tremendously big groups here, if I just have some hydrogens, I'll be able to apply enough energy to get it to rotate around. And as soon as it rotates around, it adds to the alkene. So that's kind of rule number 1. But that only applies to the diene. then rule number 2 is that the stereochem of the stereochemistry of the alkene is going to be preserved in the product, whether it's cis or whether it's trans. So when I make the product, and again I'm going to have carbons 1, 2, 3, 4, and then 5 and 6 come together, double bond between carbons 2 and 3. If those two CN groups are cis, then they will end up cis in the final product. So the stereochemistry of the alkene is preserved in the final product. If they were cis, those two groups will be cis in the final product. If they were trans, it'll be trans in the final product. And the reason for that is, whatever the stereochemistry of the alkene is, when that diene plops down on top of it, those two bonds are formed at the same time. So there's no way for cis to become trans or vice versa. So whatever the stereochemistry of the alkene is, it's going to get locked in place. Does that kind of make sense? So when you're doing a reaction of an acyclic diene, and either a cyclic or an acyclic alkene, it's pretty boring. Because you'll make your 6-membered ring, the groups attached to carbons 5 and 6 are going to end up either cis or trans, depending on what they were in the alkene. The more interesting situation is, what about a cyclic diene? So what do I mean by a cyclic diene? This molecule is called butadiene. Or no, it's not. That's not butadiene. That's this is Cyclo Pentadien. So when you take Cyclo Pentadien and you react it with a cis alkene, I'll use my same CNs. You're going to make a 6-membered ring with a bridge. So again, if I go 1, 2, 3, and 4, and 5 and 6, I'm going to end up forming 1, 2, 3, 4, 5, and 6, double bond between carbons 2 and 3. What's attached to carbon 1 and what's attached to carbon 4? This CH2 group is going to be attached to carbon 1 and carbon 4. And then what's going to be attached to carbons 5 and 6? The CN groups. And the CN groups are going to be cis, because in this case I made them cis. Now, this is a bicyclic compound that we talked about in first semester. So if I'm looking at this from the top now, if I wanted to look at it from the side, it's going to look like this. So that's two 5-membered rings fused together. So it turns out that the two positions over here, this is basically a boat conformation. This is a boat conformation of a cyclohexane ring. So there are equatorial positions and there are axial positions where the CN groups could go. And then there's a CH2 group up here. Now there's two possible products of this reaction when the two groups are cis. The CNs could go into two equatorial positions, or they could go into two axial positions. They could go into either one. So let me write those two products. Yeah, this is a boat. This is a boat conformation because these two carbons, it's not a chair. It's a boat because those two are being pinned up by the CH2. Yes, they're still both above the plane of the ring. And these two, and then these two positions are below the plane of the ring. So the equatorials are above. The equatorials are actually on the same side of the ring as the CH2. And then the H's are on the other side of the ring. So this is the, so this is basically, this is a bridge. So you can form this product where they're both equatorial and on the same side as the bridge, or you can form, you can have the CNs be axial and on an opposite side of the bridge. So those are the two positions that they can be. Now again, this is only when you have a cis alkene reacting with a cyclic diene. If this was a trans CN, then one CN would be axial and one would be equatorial, and there would be no difference between the products. You would get the same product. So only if this is cis do you get these two products. So that's what that, so that's what the, so that's what it's going to look like. So that's how the molecule is going to look. I don't even know if this is going to work. Let's see if I can project that up onto the screen with Solstice. It's probably going to crash. The other one. What am I not in? So one of these is called the endo product and one of these is called the exo product. And so let me show you. And so which is which is endo, which is exo, and how can you kind of remember that that's going to be the case. We're not seeing that. Too much technology. Now I got multiple screens. What am I going to do with that? I have no idea how to get the. I have no idea how to get this out of split screen mode over. That's kind of cool. All right, so here's the. So just okay. So here is our. Here is that molecule. Okay. So this. Do I have any? All right, I have a blue dot. The blue dot, that's the CH2 of the bridge. And then the double bond would be over here. So this position and this position are equatorial. And they are on the same side as that bridge. This position and this position are now axial, and they are on the opposite side of the bridge. Okay. So over actually I kind of like this. I have no idea how I'm going to get it back in the future, but I do like it. So over here, when the CNs are on the same side of the bridge, that is what is called the exo product. And when the CN minuses are axial and they're on the opposite side of the bridge, that's called the endo product. Now, what we would like to do is we would like to use English language for these in the same way that we would use English language for like biology. Right? Because exo means if something has an exoskeleton, the exo means that it's on the outside, whereas if it's an endoskeleton, it's on the inside. So here's how I remember that. And if you want to come up with your own creative idea, go for it. I kind of think of this bridge as creating kind of like a cylinder for the molecule. That the molecule with that bridge over here, the molecule that kind of with the bridge, we have kind of a cylinder that would go from like maybe here to over here. That creates a cylinder. And down here, these groups are kind of, the CN groups are kind of like on the inside of that cylinder, being axial. And out here, they're kind of outside of the cylinder, so that is the exo. Is kind of how I remember that. So the exo product is when the CNs are on the same side of the bridge. The endos when they're on the opposite side of the bridge. Because of quantum mechanical rules, which are beyond the scope of this course, and which won somebody else a Nobel Prize, only one of these is actually permitted, and one is forbidden. Although actually it's not really forbidden, but it's not favored. The endo product is always the major product that's formed. And we can argue major versus exclusive, but the endo product then is the major product. So whenever you do a reaction with a cyclic diene and a cis alkene, you will always get the endo product as the major product. Although apparently the reaction that we're going to do in lab today, if we raised up the heat enough, we would actually get some exo product, which is one of those things that like violates quantum mechanical rules and the world will end. But I think it's not necessarily it's forbidden. Forbidden means it's forbidden forever. Right? It's not quite forbidden, it's just not predicted. Okay? All right. So you probably, the Diels-Alder reaction here we'll continue talking about on Monday. So it will not be on the exam. Right? But we'll pick it up from here and then move into aromaticity for Monday. On the exam, we will cover all of the materials, or we will have the reactions and mechanisms that we talked about this week. So again, if you want to jump ahead of that, feel free to go and look at the reading assignments and the notes. What reactions did we do? What reactions did we talk about the mechanisms for? And you can create a list. But it will end at Diels-Alder. So 1214? Yes. It'll end at 1214. I suppose if you don't want to be overly ambitious and write that list out, then I'll probably write one out as well and send it to you maybe this evening. But I would strongly encourage you, when you get that list, to then go through and make sure you study those reactions as well as those mechanisms. Okay?
Question about
Yeah.
So, for getting from here to here,
And I'll take your take-home quiz problems.